We're going to develop the power rule. We're going to develop the power rule using first principles. Okay? So imagine you don't know, actually, you don't know any calculus at all. You don't even know what it is. Okay? And you have some function, there it is, characterized by x to the power of n. Okay? And you want to know what the slope is right at that point. Okay, now as I said, you don't have any calculus, but you do have access to an infinitesimal microscope. And under that microscope, you can see there's the function moving along right there, but it's a straight line at the infinitesimal distance. And so here's your that distance is x to the n. It's actually, well, it's not x to the n. It's the change. It's in x to the n. So we'll just call that a little d, x to the n. And here's your, instead of it being your delta x, as you might often render it, it's a little dx, and the d there lets us know that we're dealing with infinitesimal amounts. Okay, so what we're looking for then is the slope here, the rise over the run, or whatever you call it, which is this d, the small change in the value of the function, divided by the itty bitty small change in x. So now we've defined what we are looking for. So we're going to start with an example of finding the slope of x squared. So we want to find that small change in x squared for every little incremental small change in the value of x. And we do this by drawing a square with sides x. Now the area of this square is x squared. All right. Now we're going to increase x ever so slightly by an amount dx. So that means this shape is going to go up a little bit. And we're also increasing this x by the same amount, by dx. So that's going to go up a little bit. And so now here's our new x squared is this bigger square. Now the question that we're asking is, how much did it go up? All right. So what's the area of this? Well, it's x times dx. And this is going to be the same. This is going to be x times dx. All right, so let's add these two together. X dx plus x dx. All right, and the area of this bit here is dx times dx, so it's dx squared. All right, so let's add that, plus dx squared. All right, and then we just want to divide by the bottom of the triangle. So dx, dx, dx. All right, so these dx's cancel out. One of these dx's cancel out, and so we end up with x plus x, so that's just 2x plus dx. Okay, now remember, this is infinitely small. So we simply need to write that as 2x. So that's our slope anywhere along this x squared graph. All right, so that's our anchor. We're going to take that now as having been shown, and we're going to expand this to, well, what if we have x to the power of anything? Okay, so instead of a square this time, we'll have a rectangle, and this side is going to be x to the power of n. Okay, and this side is going to be x. So I'm assuming that this side of the rectangle is longer, so x must be some number greater than 1. Right, so what do we have in here? Well, we've got x to the power of n plus 1. That's the area. That's the area of our rectangle. All right, so we're going to increase this side by an small amount of x dx, and we're going to increase this side by dx to the n. All right, so let's fill in the rest of this. Now, what do we have here? We've got an area of, it's dx times x to the n. And over here we've got an area which is x times dx to the n. Okay, and what do we have in here? We've got dx times dx to the n. All right, so we're interested in the increase, because the increase is actually going to give us dx to the n plus 1, we trust. All right, so how much have we added here? We've got dx times x to the n plus dx to the n times x. Okay, and then we've got this little bit over here, which I think you can suspect what's going to happen to it, times dx to the n. All right, so we got stuff. Now we want to know how much this changes for every little change in x. So divide that by dx, divide that by dx, divide this by dx, and divide this by dx. All right, so let's work backward a little bit here. Here we got these dx's, they're going to cancel out. All right, so we end up with an infinitesimal, which by itself doesn't do us any good. So that's kind of good. Here's a dx, okay, and here's an x dx times dx to the n times dx. Okay, that's cool. So here's what we've got so far by way of summary. D by dx of x to the n plus 1 equals x to the n plus d by dx of x to the n. Now, it's a bootstrap problem because we're defining the derivative, what we will call the derivative, in terms of the one before. So where does it all end? Well, it all ends at x squared. That is n equals 2, doesn't it? Because we've got the derivative of x squared. So if we want to do x cubed equals, that would be x squared, because n is 2 in this scenario. That would be x squared plus d by dx of x squared, which we determined previously is 2x. And I'm sorry, this has to be all multiplied by x times x, and that equals 3x squared. And then now that we've got the derivative where n equals 2, we can do this again for n equals 3, and we'll end up with, I won't write it all out, but we'll end up with that's going to be x cubed, because it's always x to the n, plus x times 3x squared. Okay, and that ends up being 4x cubed, and so on and so forth. You'll find that this number keeps continuing. It's always n. Okay, and this bit in brackets then is always n to the times x to the n minus 1. And now here's where your intuition will then lead you to the generalization that d by dx to the n equals n times x to the n minus 1. And we could prove this process using induction if you really want to be rigorous about it. But if you don't, which I don't, you can stop watching right here. Like, subscribe, comment, share, check out some of the other videos, do what you like, and I was going to say we'll see you again. But bye.